So let's go ahead and talk about the elephant in the room. I know you guys have been probably worried if you haven't taken calculus or are just now taking calculus. You've been worried about the calculus or the C part of the class, but you know what? Don't worry about it. Most of the class is actually going to be algebra based because that's how we do most physics. That's how we do most calculus actually too, is it's mostly just algebra that we're doing with a couple other extra things added onto it. You will have to do calculus on the final, okay? Or on the AP test, whichever one you're taking, okay? But what the heck does calculus get us? Well, it gets us things like this. If you had some kind of a weird function that was defined here and here, but did not exist here, you get a DN or you get an error every time you put it into your calculator, you know what? Newton looked at this and he said, this is stupid. This is pretty obvious what the answer should be, right? It's pretty obvious where the answer should be. It should be the exact same as this, but here. Okay, so how in the heck do we solve this? Well, this was kind of the beginnings of calculus. Okay, so what Newton did and what others did is they said, let's go ahead and look at the limit of this function, whatever this function is, right? As it approaches this point, I'm going to call it A, okay? As it approaches A. So what they did is they ran through this equation over and over and over again, and they got closer and closer and closer to that point A. And what you end up finding is that eventually you're going to come up with a number that gets closer and closer and closer. And let's say this is 5 and this is, 3 over here or something, right? What you're going to end up coming up with as you get there is an answer that gets closer and closer. You're going to have like 2.9 here, for your y, and you're going to have maybe 4.9 for your x. As you get over this way, you're going to have 5.1 for your x, and you're going to have like 3.1 for your y. And you're going to get closer and closer. You get a number, you plug in for, whatever value for x, and you're going to get closer to, 3 for your y. So it became obvious to them that as they put this in, you can actually find answers for things like this, where you have a discontinuity. But that's not all, okay? And this is where we use it in physics, is actually trying to find change of things. So, in this instance, let's take a look at an exponential function. Okay, we have y is equal to x squared, okay? So, let's go ahead and put in some numbers here. Let's go ahead and call this 1, 2, 3, 4, right? And on this side, let's go ahead and put in 2, 4, 6, 8, and so on, right? Okay, so our function is y is equal to x squared. So 1 times 1 gets us 1, right? As you might be able to imagine, okay? And what about 2 for x? So 2 times 2 would be 4. So 2 for x means 4 for y. What about 3? If x is 3, we get 3 times 3, we get 9. So you end up with a curving function like this. What if you wanted to know the slope of this line? You're going to have a heck of a time doing that, aren't you? What you're going to find is that this thing has not one, but many slopes. Each one of these things, and then let me draw this in a different color so you can actually see this better. What you're going to see is the slope of the line at different points is going to be very different. Okay? The instantaneous slope at 1 is going to be different than the instantaneous slope at 2, is going to be different from the instantaneous slope at 3. And these lines, if you've done math before, what you'd find out is this is called a tangent, right? It's a tangent line. So what does a tangent line do? It follows a curve. I'm on the wrong marker color here, okay? It follows a curve, but it only intersects at that point, okay? This tangent line only intersects at this point, okay? This tangent line only intersects the curve at that exact point, okay? So it turns out that your slope changes. You don't have a constant or fixed slope. You have a changing slope. So how in the heck do you figure that out? Well, pretty easily, actually. To do this, if you wanted to find the slope of this line, or the function that represents the changing slope of this line, what you need is something called a derivative, okay? So what a derivative really does is it simplifies a curve down, okay, into a straighter line. It straightens out the curve, okay? And it figures out the function of a changeable function, okay? It figures out the slope of a changeable function, okay? So really, if you think about this, this thing has a higher dimension. It has to the second power, okay? What we want is a straight line, which would just be like y is equal to x, right? That would be our function. How does the slope change? It changes in a regular progression. It gets steeper and steeper and steeper as it goes. So what we need something, a function that will tell us that, which will be one dimension less than this. It'll have less change to it. So here, how a derivative works, okay? You have a function, okay, and your function is x squared, okay? What if I want to know the slope of this function? Well, here's how I do it, okay? To take a derivative, very simply, I take and I drop this number down, okay? So the way that you note, one way that you note a derivative is by putting a prime there. Sometimes you'll see people put a dot above it. It means the exact same thing. It's the exact same thing. Sometimes you'll also see people say d of the function over, change in x, right? Because we're going to look at it in terms of the change of some variable. We're going to look at it as x changes here, okay? So what I'm going to do is the prime is easier. I like that more. It's simpler to write down than d over dt or d over dx, right? So what is the change or the derivative of this? Okay, very simple. I take this number and I drop it down in front and multiply it, okay? I still have x there, and I drop this power by 1, so it's 2 minus 1, okay, or 1. So my new value is 2 to the x to the first, or 2x, okay? So the derivative of x squared is 2x. So if I wanted to find that, how does my slope change as I go along? The slope of this function, y prime, would actually be 2x. My slope changes pretty rapidly, right, as I go farther and farther along the x. It's a constant change. Okay, so let me write out the general formula for this, okay? For any power or anything here, okay, you have x to some power. Okay, so how do you go ahead and find a derivative of this function? F of x is x to the n. Derivative of it is going to be n, the old power, times whatever you had to begin with, and then your number minus 1. Okay? So if I had x cubed, so if my function is x to the third power, then my derivative of that is going to be drop my power down and multiply by it. So 3, still have x, and I drop the power of this by 1, so I get 3x squared. Okay? So that's how you basically take a derivative. No big deal. Okay? So that is the start of that. Now there are other things that can happen here too. All right? One thing I want you to see is what if we get our function, our original function was just x? Well, we have to drop the power. Okay, so let's write out what the power is. We never really write to the first, but it is to the first, okay? So if we want to take the derivative of this function, we drop the power down in front, so we multiply by 1, okay? We still have x, but now we drop the power by 1 value, right? So it was 1, so now it's 0. Anything to the 0 power is actually 1, okay? So if we had our function, right, y is equal to x, you end up with, a graph that looks like that. There is no change to it, right? It's constant. It's unchanging, okay? So what is the slope or the change of this line? There isn't one, okay? So what we end up with is that first power drop down, 1 times x to the 0. Anything to the 0 power is 1. So our change is 1. We don't really have a change to the slope. It just keeps on going at the same rate, right? It never changes, okay? What if we have a function, x to the 0 is my original function, or 1 is my original function, okay? Okay, so what the heck do I do? This is basically just x to the 0, right? 1 is. So if I take the derivative of this, well, I drop down my old power and I multiply 0 by x and then drop it by, well, it doesn't even matter at that point because 0 times anything is going to be 0, isn't it? So if you have a constant, if you just have some number, okay, 1, you have 2, sometimes in physics we represent a constant as c, right? If you have an unchanging value, what is the derivative of it? It's 0. The derivative of a constant is 0. Don't forget that one, okay? So it's a weird exception. It's not really an exception. It does the exact same thing, but it is important to know that when you have a constant, if you take a derivative of it, you get 0. Now that is important, okay? What else do derivatives get us? Well, you're looking at the change of a line over time, right? So let's go ahead and draw out our axes, and let's draw out some kind of a crazy shape, maybe to like a third power or something like that, where it does something, I don't know. You get something where you have these peaks and valleys to it, okay? So if you look at the derivative here, it'll give you the slope at that point. Derivative there will give you the slope at that point. But look here, at that point right here, your tangent or your derivative, your slope of this point would actually be 0. Same thing down here for a minimum point. It would be 0. Over here, your maximum would be 0. So sometimes you can actually take your function, right? Find the derivative of it, and if you set that equal to 0, wherever it is equal to 0, you will find a maximum point or a minimum point to your graph. So you can find local minima and maxima by using derivatives as well, which is pretty cool, very quick, and extremely functional for a lot of things rather than trying to hunt and peck and find everything along that entire curve. One and done. Okay? So that's derivatives in a nutshell. We'll get into some more stuff later.